recording and officially welcome everyone. Any other homework things that you want to go over while I have this up, folks? Homework, what is this, 4? Yes, homework 4 is due Wednesday evening. I do have office hours tomorrow, as usual. No office hours this week on Friday, however, as I sent out via email. Zoomers, any questions from you? I'm looking at the homework. Chris is good? All right. I'll share the screen while I'm at it, since I probably want to see the rest of the stuff. Going once? Going twice? All right, homework's done. So we have, it feels like it's been a while since we talked about this stuff, but we have a little bit of Unit 4 to finish up today, and then on to Unit 5. You've been seeing my emails about your homework 5. You all should have received my feedback on your plan. And if I noted at the top of your plan that you only have 1 point because I need some more information from you, then please revise your document or answer my questions, send it back to me via email. And then once I have agreed with you on what you're planning on doing, then I'll give you your 2nd point, and you can be working on these things. The next thing you have, though, before homework 5 is due is a formative assessment. That's due next week. I think that one's number 5, maybe? Does that sound about right? We're getting there, because there's only 6. Everything ends at 6 in my classes, so we are heading towards the end. So that will describe, formative assessment will describe what we're talking about today, as well as Thursday. That'll be due next Monday. And then homework 5, the individual data analysis, will be due a week after that. My intent is to be able to turn them around to you within a week or so that you have plenty of time to tackle any revisions if you need to do so. Revisions are optional. So if you get your score back and you're like, I'm good with this, you don't have to revise it. If you get your score back and you're not good with it, then you can revise it, and the revision will be due by the end of finals week. All right, so we were talking about, I think we were just starting to talk about quantile regression. Does that sound right? Give or take? All right, so the topic of this lecture here is basically potpourri, or a grab bag of other kinds of related techniques for outcomes that are continuous, and they have some degree of skewness and or a boundary at 0, but they don't conform to a traditional normal distribution. So I think what we had talked about before were a couple options. Gamma is a response distribution. So gamma is used for things like minutes of exercise or costs, things that can have very large values because it can take on whatever level of skewness that it needs to. A log link is used with gamma to keep the predicted outcomes positive. Another one is log normal, which is an identity link, and the residual distribution is log normal. Meaning what you're saying is that if you take the natural log of your outcome, then the log of those residuals has a normal distribution. This one is nice because it actually is the same thing as just transforming your data. So this is a reasonable compromise if you're dealing with an outcome where you feel like you need a generalized model, but for whatever reason, it's not going to work. So for example, in my longitudinal class, a couple students have count outcomes that they're trying to fit longitudinal analyses to in the context of having a bunch of other variables modeled over time in their analyses, and they're running into convergence problems or things that last for days and eventually don't crap out. So taking the log instead is a reasonable compromise. At least you're saying the residuals have a log normal distribution, which may be plausible for outcomes with this type of skewness. This one doesn't have. Log normal is also bounded already at 0 in terms of a distribution. So this is not for something that includes zeros. If your count includes zeros, you'd have to add 1 to be able to take the log of it to be able to use this. And then if you have zeros, you may also need to have a separate submodel that predicts whether or not you have an outcome that's not 0 versus 0. So like if it's minutes of vigorous physical activity, you would have something like, did you move during this hour? Yes or no? And then if you moved this hour, how much did you move? Something like that. So the same concept as the zero inflated or hurdle models that we had for count data, just for continuous outcomes in terms of the amount part of the distribution. So I think we had finished with all of those, but just to reorient us to where we were in the discussion. Then we're into something new. Ready for something new? Cool. Thank you for nodding so enthusiastically. Yes, we are ready. We are here. I have had a lot of caffeine today, so I'm excited. Yes. Diet Coke today, changing things up. All right, I'm on slide 17 of lecture 4. That's where we are here. So a better way of handling outliers. I want to talk about quantile regression. It's not technically a generalized linear model, but it goes with this unit because this is a way that you can address not just outcomes that have skewness, but outcomes that have skewness as a function of having outliers. And I generally don't like the idea of an outlier analysis that involves making arbitrary decisions about which data points to remove. So you'll see some very well-meaning textbooks have entire chapters on like data cleaning and outlier checking and that kind of stuff. Be very, very wary of those types of strategies in the absence of a model. You can't just look at a distribution and say that's an outlier, because the assumptions that we make about what the errors are supposed to look like is not about the marginal distribution, it's about the leftover part. And we don't know what the leftover part looks like until we have a model. So you can't tell if something is an outlier just by staring at the data. If you have a value that is aberrant, meaning it's far away, the thing you would want to be concerned with is influence on the solution. So like you've all seen the plots like in intro stat where you have like a cloud of points and then there's like a point way out here. And if you try to fit a regression line through the cloud, maybe it's flat. But if you have that one point, maybe it tilts it upward. And so that would be the concern, is that like one case would have an undue influence on the solution. But if your model is able to explain why that case is so far away from everyone else, when that case becomes a residual, it may not be that weird. So you can't look at outliers marginally. The other part of it is that if it's a valid observation, then you really have to be like, it's a subjective decision to kick it out of your data set. And you would want to, at a minimum, describe what happens with it and without it, particularly if the story changes. So I had this in my dissertation, for example. I had 155 older adults, and the scores for 3 people on a measure of processing speed were enough to take a relationship and turn it into significantly positive from 0. And if I removed those 3 cases, there was no relationship. So that was the story. I went with the not 3 cases, but there's a footnote that says like there's 3 people in here that would have changed the outcome, and I wasn't comfortable letting those 3 people dictate the story. But at least if you're upfront about it, you can decide, your readers can decide whether it's reasonable to kick cases out. But as an alternative, we don't have to kick anybody out. We can do something called quantile regression. And the way that quantile regression works is based on switching out what we're predicting from the mean to some other point on the distribution. So we can predict median as a starting point, which is the 50th percentile. You might have heard of this as median regression as well. The way that this works in terms of figuring out what the best answers are for your fixed effects, your intercept and slope, is rather than minimizing the sum of squared residuals, which creates like a quadratic type function that we can use calculus basically to figure out when we're at the bottom of that. Instead, the function that's being minimized is the absolute value of the residuals. So you end up with this thing. The consequence of that is that we can't get standard errors directly as a part of the estimation process. So we have to do something else to get the standard errors. And you may have heard these words before, bootstrapping. Does that sound familiar? Maybe. You at least heard the words if you don't necessarily know what it was. The idea of bootstrapping is that you are trying to use your one sample to recreate what the sampling distribution would be for your answers. So the idea of a sampling distribution is if I did the same study over and over and over again, same sample size, same kind of people, I would have a range of what my results would be. For each parameter, I'd have like the slope isn't going to be exactly the same. So what it does in bootstrapping is sample from your current one sample with replacement multiple times, each time figure out, say, what the slope would be, and then you have a plot of the range of the slopes that you would get from this process. And you can use a middle value as your point estimate, so it doesn't have to be the mean, it could be the median. And the standard error then, or the confidence interval around that slope, is what you would have in that result. So bootstrapping is one way to do this. One caveat with this is that whenever you're doing any kind of resampling type process, you will not get the same answers back because it's a sampling. So it's going to change every time you run it. So in order to create reproducible results, you will have to set a random seed, which is basically information for where the random process starts with respect to your computer. So for those of you who are part of Gen X, you might recognize the random seed in my example is 8675309. Does that mean anything to you? Chris, I know you're part of Gen X, aren't you? I'm calling him out. For sure. Do you know who Jenny is? 8675309. Just type it into YouTube when you get home, okay? It will tell you. It's an 80s pop song. It's a song lyric, yeah. It goes 8675309, yeah, and that's how it goes. So, Tommy Two-Tone, I believe, one-hit wonder. So yes, Jenny is my forever random seed. Oh, and Chris's wife is named Jenny. How fitting is that I called him out? I didn't even know that. How about that? So yes, you will see this number so that I can get the same results every time I run this. In practice, you would want to save the seed that you've used so that you can reproduce your results, but not necessarily use the same one for everything. And the packages that we're going to use for this is QuantReg in SAS. Stata has a couple of routines, and I found something in R. Although the capabilities of SAS outstrip what the other packages can do, so I've got some SAS output in the example to show you based on that. So one thing that is really nice about this is that it's generalizable beyond just predicting the median. So the reason to predict the median is that it is less sensitive to outliers because it's just literally the middle value rather than the mean, which can be dragged by the outliers. But you can predict any percentile by asking for it to differentially weight either side of the absolute value. So the way that I would think about this is that these methods allow you to essentially answer what would be on the surface a predictor by outcome level interaction. So I have an example here. Let's say that you have academic performance of some kind of measure and you want to help students do better. Well, odds are good if you have students who need help, you're more interested in helping them than students who are doing just fine. So if you have a distribution of possible scores, then you can ask, does my intervention have a stronger effect on the low end of my distribution than on the high end? Does it help the low people more? So you can actually fit a model that says, like, what does my intervention slope say at the 25th percentile, at the 50th percentile, at the 75th percentile, and look at differential effectiveness of a predictor at different points along the distribution. So I had a student that I helped at KU, I think, with a question like this, and I pointed her towards quantile regression. An example from my own previous research, so I used to live in the world of cognitive aging, where we had a lot of speeded tasks. And the question was, does age predict response time to a speeded task to a greater extent amongst the slower people than amongst the faster people? So people who are fine, I would expect age doesn't matter. Among the people who are showing some kind of deficit, perhaps that deficit is related to how old they are as a proxy for whatever disease status or other types of health concerns. In my example, 4B, we're going to look at houses. We'd looked at that a little bit last time, like 2 weeks ago maybe. It seems like a long time ago in my head. Does square footage matter more if you're selling a cheap house or than if you're selling an expensive house? So amongst very inexpensive houses, do you get more of an increase in your price for more square footage relative to what you would get amongst expensive houses? So the same type of ideas here. I have a note that I've seen a little bit of work extending quantile regression to multi-level settings. That's harder to do and tends not to be as readily available. So it is technically possible, but it's much less common. So that's one potential bummer about this. All right, let me show you then what this would look like. So any questions so far? No. Crystal clear? She's not. Yeah, absolutely it is. All right, I know it's not, but I feel like I got to fill the space. So I'm on, what am I on? Page 7, example 4B that we've been working through. So we're predicting the same data set here, Just as a reminder, what's in every model that we looked at so far, we're predicting house prices in the 100,000s, and we have whether the house is new, the number of bedrooms it has, the number of bathrooms it has, and then a linear and quadratic effect of square footage. And across alternative models, earlier in this handout, we saw the effect of square footage go from negative to positive in terms of the quadratic. And the reason for that is going to become a little bit more clear as we look through these quantile models and what is the effect at different points along the distribution. So I have SAS here because I'm using SAS Output because it's the most complete. But we also have here sqreg is the command in Stata to do this. So we have the outcome is price. I've got all of my predictors here. And then in terms of the options that go into the analysis, I have what quantile I want. So I'm asking for the 50th percentile, the median. The number of replications that I want, and that's with respect to getting the bootstrap standard errors. And note that before that, I have a command called set seed that controls the random seed for the resampling. And of course, Jenny is my random seed forever. Same thing in SAS. The model statement is here's where your predictors would go. You can tell it what quantile you want, and you can tell it what seed you want within that. And then we have options related to the resampling where I'm asking for 500 replications. So the output that you get back, whether you look at SAS or Stata, the numbers are a little bit different with respect to the standard error, but the coefficients are largely the same. The big difference is that we're talking about predicting the median rather than the mean. So the intercept, for instance, in Stata is 133. That's the median home price for a reference house that is old with 3 bedrooms, 2 bathrooms, and 1,500 square feet. So then the difference between old and new houses increase the median home price by $32,000, which happens to not be significant according to Stata. If I have only 2 bedrooms, that actually increases it a tiny bit, also not significant. If we look down at the effects of square footage here, we have a positive linear slope and a positive quadratic slope. We talked about this before, but since it's been a while, let's go back into it. This pattern of positive, positive, what kind of function is this creating? Positive linear with positive quadratic. This is like a hand question. Do I need to get paint out? That's what I did last time. What is happening to my linear slope as I move further up the variable? Is it becoming more positive, less positive, more negative, or less negative? More positive. So the effect of square footage is getting stronger the higher up square footage you go. So it's like an accelerating function. And by how much stronger, what's the rule? What do I got to do to my quadratic coefficient to interpret it? Times 2, that's it. Twice the quadratic is how the slope changes per unit x. Times 2. The other way I can think about it is that this coefficient represents half of the second derivative. To get to the full second derivative, we have to multiply it by 2. So square footage matters even more in predicting the median home price in bigger houses. That's how I would talk about that. My model, I have an f-test for the overall contribution of the model. I could potentially do some sort of R-squared type thing as well. I do note that we do get different standard errors, like I said. So for instance, the median home price for the reference house is $133,000. Standard error of 7.3 according to SAS, 7.29 according to Stata. And in R, I could not figure out how to get standard errors, but it would give me confidence intervals. So I was like, fine, that's close enough. At some point, you just have to give up fighting. So in R, I am using a function called RQ. And tau is how you tell it what quantile you want. And then formula gives you your model as usual. This package had a whole bunch of options to do things, and I didn't spend a lot of time digging through it, but presumably there's the same types of customizations in terms of how you would get different ways of computing standard errors and so forth. So what about the median? Well, there's nothing special about the median. We can ask it to do different things. So what if I want to predict low-priced houses versus relatively more expensive houses? I can predict the 25th percentile and the 75th percentile. And these numbers are arbitrary, right? Could I predict the 27th percentile if I wanted to? The 39th? Sure it could, whatever you want. These are just sort of prototypical lower and higher examples. So in SAS, I can list multiple choices after quantile. I can also ask for a walled test for the set of predictors within each submodel, as well as whether they differ. So you're allowed to ask, is the slope for, say, whether the house is a new construction, is that slope stronger in less expensive houses than in more expensive houses? So does my intervention matter more amongst lower performers than high performers? Those types of questions. So here is SAS output first. So predicting the 25th percentile, here's my solution. So at the 25th percentile, the house is 101. At the 75th percentile, the house is 145. And we can interpret the rest of these pretty much in the same way. Looks like square footage has a positive slope with a positive quadratic in both of these. These are the omnibus test of whether the slopes are different. So this is an example of comparing one slope at a time here. You could do that for each of them if you wanted to. Stata has some interesting stuff with respect to this. So here's SQReg, where I'm asking for 25th and 75th percentile. So it gives me, within separate boxes in my output, what the 25th and 75th percentile solutions would be. I can ask for walled tests at each of those. So one thing in Stata code that I don't think you've seen before is in models where there's multiple submodels happening. So like, for instance, this term right here, c.new is what the slope is called. And so I'm asking, what would it be if that slope were fixed to 0, and this slope were fixed to 0, and this slope were fixed to 0? So I'm creating a multiple parameter walled test, lumping the slopes together to get a joint test. But then the thing in brackets specifies what submodel I'm referring to. So this is the slope of new construction in the 25th percentile instead of the 75th percentile. So there is an option in Stata if you're not sure what your code should look like, how to refer to something in your model. The words that you can type are coef legend. I can't spell legend correctly. There we go. COEF legend. What that does is, instead of numbers in your output, it spits out a table of how it refers internally to every single parameter. Then you can take that language and tell it what to do with your parameters. Make them equal, make them 0, what have you. So that's a useful tool when you're not sure how to refer to something inside Stata. And then Stata also has this thing, IQReg. What this does is directly give you the difference in the slopes. So how different is each slope in predicting the 75th percentile minus the 25th percentile? So the 25th is the reference. So how much different is it if I predict the 75th instead? So all of these are slope differences. So you don't have to write out all the lincoms to get them. You can just ask it to write the model within this version. Each of these takes like a minute or two to converge, by the way. So these aren't instantaneous results like we're used to. It does some kind of pseudo R-square. I'm not sure what kind that is, but we can look it up in the documentation if you're curious. In R, it lets you ask for multiple quantiles as well. So the C thing, to link together different pieces, I'm asking for the 25th and the 75th using the RQ function here. So I get the solution for the 25th, the solution for the 75th as well. So beyond just this is predicting the median or this is predicting the 25th percentile, everything else works exactly the same. So it's not a heavy lift in terms of there's no link function, there's no alternative distributions that we have to worry about. We're assuming the residuals are normal, but it's less of an issue if we have not normal because we're using resampling to get the standard errors rather than distributional assumptions. So it's a robust technique, I would say, broadly construed. All right, questions so far? Yes?
So regarding the seed,
Mm-hmm.
is there any enough number of seeds?
Like a limit to how many of these you can do? Is that the question?
I mean the minimum and maximum, or?
Well, I think 0.1 would be the minimum probably, and 0.99 would be the maximum that you could ask for. I don't know if there's a limit to how many you can have at once.
Oh, I mean the number of the seeds.
The seeds?
Yes, sorry.
I think that if you ran this again with a different number, then that would change the seed. But I think that as long as this is like active, that everything that follows it would have that seed. I'm not 100% on that. Anyone who's better than R can correct me. If I set the seed, does it stay set or does it go away? It's an empirical question, right? Because you can run like two things and then like see if it changes if you change the seed. So I think it should stay because like set to me means like make it this way, you know, but I could be wrong. Where I thought you were going was how many of these can I have? And I found a thing in SAS that I thought is super cool that I could not find in the other packages, so I just have SAS output here. So in Quant Reg, rather than saying I want the 25th percentile or the 50th percentile, process means give me all of them. So this took like 5 minutes to run, but it produces these really cool plots. So what I have for each of these plots, the y-axis is the size of the fixed effect. The x-axis is the quantile. So it went through and did all of them. So for instance, new construction, the squiggly dark blue line here is the point estimate of the slope at every quantile, and the shade around it represents the confidence interval. So it looks like the slope is just shy of significance, meaning it's not quite overlapping 0, but it's positive the whole time, but it looks like it might be getting less positive as this goes on. So new construction looks like it matters a little less the higher up you go. Some of these are quite noisy. Some of them are quite consistent. So for instance, this is 2 bathrooms versus 3, pretty much the same answer, regardless of where you go in the distribution. The linear and quadratic effects of square footage, though, I thought were interesting. So it looks like there is a positive linear effect of square footage. So bigger houses sell for more money. And 0 is down here. But look at the quadratic. 0 is this line right here. So amongst lower priced houses, it looks like the quadratic is heading negative, meaning that square footage matters less the higher up you go. But then it switches over to positive and becomes significant in the middle here, and then we get a lot of noise where it's not detectably different than 0. So like the answer you get, the conclusion that you would come to about whether there's a quadratic slope on square footage depends on what point in the distribution you're predicting your outcome. So I thought this was really cool. So I wanted to show it to you. Question?
So if we do not use a quantile regression, then we are assuming the predictor's effect on the outcome is always the same.
I think that's fair. Yeah, I think you are assuming that predicting the mean is all you need to do. Like if you predicted any other point, then the answer wouldn't change.
Mm-hmm. That means like the effect can change according to which point you're at the outcome level.
Yeah, it's an empirical question whether or not the slope is consistent in predicting differences at every point along your distribution.
It's not the slope itself change.
The slope itself is different at every point. Like if I'm predicting the 10th percentile versus the 90th percentile. And so this is tracking the change in the slope as I move up my quantile of my distribution, is what this is showing. So yeah, and here's some words. So the whole handout, as usual, sample results section. Using, I think I used SAS Output for this since it was the most consistent. There we go. So you don't have a homework on this. I just wanted to show it to you because I thought it was cool. So no homework on Unit 4. No homework on Unit 5 either because you're doing your individual data analyses instead. So I used to have a homework on that it was about pancakes and crepes. You can ask people who went through the class last year. It was brutal. You would not think that homework about breakfast would be difficult, but it was. The reason is because the thing that we have to do next is, I think, less necessary amongst the cohort of people in my classes relative to what I had before. So we're heading into multivariate land next. In psychology, like repeated measures ANOVA is everything. And so I wanted to make sure that folks got really comfortable with that. That's less of a thing in the analyses I've seen people do at Iowa, particularly in the College of Ed. So I'm focusing more on path models this year than on repeated measures kinds of stuff. So trying to adapt to the times, as it were. So I have one more slide here on sort of other things. Like there's one other thing that you can do if you are not sure what kind of generalized model or if there's not an obvious choice. You can ask for adjusted standard errors. So there are what are known as robust standard errors that are available within most packages. They are going to take, they're going to incorporate the patterns in the data rather than assuming that everything is perfectly observing the distribution it came from. So these will be oftentimes higher because they're more realistic. And some folks would say that you should just default to using these. I don't go quite that far, in particular because then you get even more differences across programs based on how these things are programmed, but I wanted to make sure that you knew these existed. So in Stata, for instance, you can ask for robust standard errors. You can ask for resampling standard errors via bootstrapping or jackknifing. Jackknifing is when you leave one out. Bootstrapping is when you sample with replacement. So they're analogous in terms of how they work. These are sort of large data techniques. If you want to use these techniques with small samples, there's adjustments that need to be made. And the term sandwich errors or sandwich estimators, you may see that word in this context. That involves, like, basically there's, like, the bread is one thing, and then there's, like, the meat of it. There's an analogy that goes with this that I've never fully understood. But if you look up the word sandwich, that's the idea that they're getting at, as a robust correction for deviations from distributional assumptions. One other thing that I want to mention, because I feel like this is commonly misunderstood, and also to put in a plug for my fall class, is the idea of cluster-corrected standard errors. So there are situations in which you have clustered data, but you don't want to. So for instance, you have hypotheses or research questions about individual student performance. The only way that you could get enough students is to sample from multiple classrooms or schools, but you don't really care about classroom or school differences. Well, some folks would say, well, just do a clustered sampling correction on your standard errors, and you'll be fine. So this is a process that adjusts the standard errors for the relationship between people who come from the same cluster unit. So the term for that is dependency, what we're going to start talking about today. Dependency just means correlation. It means that observations from the same sampling unit probably have residuals that are more correlated than observations from different sampling units. And so this process of adding in cluster-corrected standard errors is designed to fix the problem of correlation in terms of what the model for the variance says your standard errors should be. Well, that's all well and good, except what it doesn't fix is that the answers you get themselves are probably incorrect. In clustered data, any variable that is measured at the lower individual level also likely has information at the higher group level as well. So if I'm a kid who's lucky enough to have a wonderful teacher, maybe I do even better than I'm expected to on my assessments because of my wonderful teacher. But guess what? Everyone else around me has the same wonderful teacher. So to the extent that performance, if you're thinking of it as like a student characteristic, is also a cluster characteristic, then we have a cluster level relationship between those variables in addition to a student level relationship. And this idea of cluster corrected standard errors cannot fix that problem. So in my classes, I call this a problem of smushed effects, meaning that you've taken a variable that should be two different variables and you've only fit one effect for it. Necessarily, the two effects it should have are going to be sort of smushed together. A synonym for this in the literature is conflated effects as well. So just fixing your standard errors if you have clustered data is likely not enough. You also have to address the potential that we have different types of information in your predictors that have different types of relationships. So the class I'm teaching in the fall is multi-level models for clustered data, which will talk about all of these things in terms of how to address hypotheses about cluster level information as well as person level information simultaneously, as well as their potential interaction terms. So just a plug for that. The fall class is going to be at 12:30, I think, and I'm doing it the same way. So hybrid, Zoom link, recording. Show up if you can, that would be great. If you can't make it, you can still be in the class. So I'm being ultra flexible because you all have shown me that there are many ways to succeed if you want to. So I'm willing to continue doing that. All right, any questions about that? Zoomers, we hanging in there?